take what you care about and you move it around, ideally in a medium where it is difficult to be followed.
Welcome everyone to the Industrial Security Podcast. I'm Nate Nelson. I'm here with Andrew Ginter, Vice President of Industrial Security at Waterfall Security Solutions, who's going to introduce the subject and the guest of today's show. Andrew, how are you?
I'm very well. Thank you, Nate. Our guest today is Ian Schmertzler. He is the president and co-founder of Dispel, and he's going to be talking to us about using moving target defense in cyber-physical systems.
Then let's get into your conversation with Ian.
Hello, Ian, and thank you for joining us on the podcast here. Before we get started, can you say a few words about yourself and about the good work that you're doing at Dispel?
Thank you for having me on. I'm the president of Dispel, and I am one of our principal investigators on 3 projects that are taking place at the National Cybersecurity Center of Excellence. And I'm also the vice president of the National Defense Industries Association's New York, Connecticut chapter. My role on a day-to-day basis at Dispel is largely making processes efficient at scale.
Our topic today is moving target defense. Now, before I heard you speak the first time at a recent conference, I had no idea that, what moving target defense was. I had no idea it existed. Can you, give our listeners an intro? What is this thing? What is moving target defense?
Okay, so let's start with the problem that almost anyone who's listening to this has had as a child, which is they are standing in a field full of snow, or they're on a dodgeball court, and someone has a snowball or a ball and they're thinking about throwing it at them. You have 2 choices for how you can protect yourself. You can stand there and hold up a lunch tray and just hope that you can block the ball being thrown at you, or you can run around. And that, in a nutshell, is a strategic comparison between one approach, which is you remain stationary, and that's known as static defense, where you invest in a wall and you hope that your wall is effective against the attack being launched against you, and moving target defense, which is where you take what you care about and you move it around, ideally in a medium where it is difficult to be followed.
So that's a lovely analogy, but we're talking, computers, we're talking automation for industrial systems. Can you work with me? How does that analogy apply in the space of industrial automation and security for industrial automation?
So we should answer that in 2 parts. Let's start with the question of how do I solve this on an individual device? What am I trying to achieve with that? So if you had a processor that always ran the same process in the same fashion and queried the exact same location in memory each and every time, you created a pretty predictable route by which an attacker could write a very simple virus and say, right, shuttle yourself in exactly here. So the first place moving target defense shows up is on the box itself with, I'm going to randomize where I save things back down to each time I perform a process.
Maybe it's just because Ian is making it sound simple and straightforward, but moving target security thus far is kind of sounding pretty interesting to me.
It does. And I know some of these techniques by a different name. So he's talked about moving target in hosts. And, I didn't know what that was because I know it by a different name. I mean, one of the techniques I think we're talking about here is what I mentioned, address-based randomization. This is where, in an operating system, most commonly Windows or Linux, when you load a program and you start executing it, Outlook, Microsoft Word, your email reader, whatever, your web browser, when you load that program, instead of loading it into the same virtual address space all the time, you've got, 64-bit processors have a lot of address space to work with. They invent a tiny little virtual machine. This is how the operating system works. They give you virtual memory. And instead of saying, here it is, it's always the same, they put the stack in one place, they put the libraries in another place, and then they dynamically link it all together and they run the program and it works. But if a hacker gets in there with a buffer overflow attack, the nature of the buffer overflow attack is you've got to put a return address onto the stack. You've got to overflow the return address onto the stack. And then when you execute that, when you return to that, you're executing code in the stack, but the stack is moved. Or you're executing code in a library, but the library is moved. And so you can't find your targets anymore, and buffer overflow falls apart. This is something that took a long time to get into sort of standard in operating systems, but it is now pretty much standard everywhere. And it sounds like he's got an analogy of this happening in the network space, which is what I think we're digging into next.
It sounds like you're saying, the IP address on every PLC, every computer in the system is changing constantly. The ports, the TCP ports that we're connecting to are changing constantly. Does that even work? How do you find anything?
It doesn't work. So that was something that people tried in the early 2010s, late 2000s, excuse me. And then what people concluded was this isn't going to work even for people talking to one another. It's too difficult to assert that every single device inside of an environment is going to be able to handle that. So what instead happened was people began to build networks composed of traffic nodes, which were virtualized. And over time, you would destroy a traffic node and replace it with another one. And this worked for protecting the connected assets, because if you look at what the attacker has as their perspective, they're trying to find A or B or C, and those assets are talking to one another. Well, how am I going to do that? I'm going to do that using a clustering algorithm to identify the patterns of association between A and B or A and C as one that would identify a target. And the way you break that is you start having B talk to a random virtual machine. And then a little bit later, it's talking to another random virtual machine, but in a pattern that is not itself unique. It looks like any everyday person, for example, going on and watching a YouTube video or something of that nature. So you break the behavioral identities of the assets that you care about by creating this network that is shifting over time in between them.
So that all sounds plausible in theory. Can you give me a concrete example?
I can. In fact, the use cases and applications track the history of how aggressively moving target defense got implemented in the industrial control space over the past decade. So most of the people who are listening to this deal with either NERC-CIP or IEC 62443 or perhaps NIST 800-160 Volume 2. But in most of the standards bodies that you're going to be reading through, you will find a section that says, chapter and verse, thou shalt have a disposable intermediate component between you and the device that you are accessing. And it is at this juncture that we introduce this concept of remote access, which could be machine to machine, but more often than not for the implementations where you first saw moving target defense, it was a human to a machine. Now that disposable intermediate component was a virtual desktop in almost every instance. So what was happening there was at the end of a person performing their task, you were supposed to destroy the virtual machine and then power cycle your hypervisor. And what you were doing in that case was shifting the plane of attack that someone had to go through. So they were going through, let's say they were punching through initially, they were working the problem. Well, they only had a short period of time where they could work the problem before the domain in which they were sitting disappeared. And they'd have to wait until another opportunity arose where the person was trying to come in for them to try and work the problem again. That's moving target defense light, I would say. That's what people were doing as soon as they could. The next step, which is a very concrete one, you'll find it in the NCCOE's papers on manufacturing. You'll also just find it every day, is in water in particular, is you'll find that people are saying, okay, I need to have a vendor come in and work on this critical asset, but only temporarily. So here, moving target defense means two things. Moving target defense means that you want to prevent a third party from seizing control of your assets or infecting your assets. So you're going to do that using a disposable intermediate component, but also preventing this vendor that you've paid from potentially making a mistake and coming in when they shouldn't to do work on stuff, or the next day they think that they're going and working on another customer, but in fact they've gone into your system, which often as not is what causes mistakes in work. So what you have here is you have not only a disposable intermediate component, which you'll typically see supplied. So that'll be, I'll spin up my virtual desktop for you, but also I'm going to stand up a network temporarily for you to come on in to work on my environment. So you'll find that people on their own will have manually built a couple of traffic nodes and linked them together with usually OpenVPN, and then tied them back to their own environment. And then while the person is doing their job, they'll be coming through this thing. And when they're done, the person shuts down everything. Now, when someone needs access again, they're going to build that entire environment again. And when they do that, because they're building these virtual machines, usually on a public cloud provider, it's going to be it's going to present not only a different IP address, but it's also going to be in a physically different location on a physically different server from the last time it was stood up.
Andrew, I like the idea here, although admittedly I'm getting a little bit lost in the details.
Let me take a concrete example. The NERC CIP standard says that if you have interactive remote access, where you got a person out on the internet coming into a power plant, you need a VPN, of course. You need two-factor, of course. But you VPN and you two-factor into what's called a jump host. And this is a host usually on the IT network or in a little DMZ network. And you log into the jump host. And from the jump host, now you can log into the control system assets. So you don't log into the control system assets directly from the internet. You land in this jump host. Now, Ian was talking about the jump host being virtual. NERC CIP, in my understanding, does not require that the jump host be virtual. It can be a physical machine that sits there all of the time. The problem with that, as Ian kind of alluded to, is that if somebody, let's say, sneaks into that jump host, gets a little malware, a foothold on there, during a session when someone has legitimate access, you trick them into putting some malware on the jump host somehow. And the malware phones home. And now the bad guys have control of malware in the jump host. The legitimate user logs out, goes away, does other things, and they still have control of the jump host. What Ian is saying is that what he saw a lot of people doing, and a lot of it is done manually. It's not required by NERC CIP, but it's a good idea, is make the jump host virtual. And when the user logs out, delete the virtual machine. It's gone. Yeah, there's malware on it. Too bad, it's gone. And so the adversary cannot use that remote access asset between sessions. They're trapped into whatever little session they can get, and then the whole thing disappears. And he's saying that, he sees people doing this in other domains, standing them up, these jump hosts up, not on the IT network, out in the cloud in a completely different country. Who knows where the cloud is going to put your virtual machine from case to case. So this seems to be the first step towards this moving target that he's talking about.
Cyber attacks with physical consequences more than doubled in 2021. For industrial victims, the most common consequences were production outages at multiple sites. Most of the attacks were ransomware. And 2021 saw the first cloud-based ransomware attack. That attack compromised 1,500 businesses in the space of 45 minutes. These and other insights are included in a new threat report, co-authored by Waterfall Security Solutions and the new ICS Strive Industrial Incident Repository. For your copy of the report, please visit icsstrive.com. That's ICSSTRIVE.com.
That kind of makes sense. Engines to build virtual machines, lots of different places, hard to find without, any sort of pattern to them that makes them easy to identify as targets for the attackers. But are we still talking, remote desktop platforms for remote access? What's the application here in the industrial space?
Okay, so the distance between the theoretical abstract, and the sale of a product and the creation of a business is the answer to that question. So a whole lot of people would look at this and say, I get that in concept. How the heck do I apply it? And the end solution had to be one where, okay, we'll stay as a network engineer briefly now. What does the end product look like / solution if you need to get a human to a machine or a machine to a machine using moving target defense? With a human reaching a machine, you are going to have a network which is shifting over time, of which one of the components is going to be a virtual desktop. And the virtual desktop will be a workstation, which, because of it being a workstation, you're going to have it remain static. But the rest of the network needs to be able to move during the connection. If it's a machine to another machine, what you need just a network that's moving around over time. And you need between these two machines, at the edges of these two machines / the networks that they are part of, a device capable of locating a moving target defense network that's been provisioned for it and establishing an initial connection to it. So that's the core thing. What does a solution look like in practice? In practice, it is almost always you have your cyber physical system. Adjacent to it, you are placing a small device which has two network interfaces on it. On that is a piece of software responsible for reaching outbound only to establish a connection to a moving target defense network. From a consumer's point of view, what they're seeing is usually a dashboard bolted onto an engine provided by, take your pick of whichever supplier of moving target defense you're dealing with. And that interface looks like what they're doing is they're assigning a person or a device access to another device. So you'll see in this regard, a lot of solutions applied towards remote access problem sets. If you're dealing with something inside of the perimeter and applying moving target defense inside of the perimeter, you're not, at least I have not seen that happen outside of very sophisticated large-scale institutions.
So you're saying there's in a sense two broad application areas. One is remote access and mostly for people, and the other one is machine to machine. The machine to machine sounds like you need one of these bump in the wire devices for every device in your network that is worth protecting, and possibly every device in your network that needs to communicate with any of these devices worth protecting. Roughly every device in your network. Is that fair?
The first iterations of that certainly were the case, but that just was not commercially viable. So what people took to doing was they would position on the OT DMZ a single device, and then you would work the problem of establishing whitelisted access between any given device on one side to any given device on the other. So it's the same thing that happened with SD-WANs, except now you have a moving target defense SD-WAN. So at the perimeters of your network in the on the DMZs, you're going to see devices / software capable of brokering these connections.
So that was, in a sense, that was a hard fit. The easy fit, it sounded like, or the easier fit was for remote access. I mean, maybe, instead of work the theory any further, I mean, you folks, Dispel works in this space. Can you talk about, the products you have for the industrial automation? What's real out there today?
Most of this is indeed remote access for humans into devices. Over 1 trillion gallons of water this year at the moment is running through a system that is remotely maintained using Dispel, because we're providing a cyber resilient connection down into systems that is a moving target defense platform. Where you'll also see a lot of it is in manufacturing and maritime systems. The other, which is the problem set of machines talking to other machines, is something that no one was buying 3 years ago or 2 years ago for that matter. It is an easier problem to solve from a networking point of view, but then people realized that if they could unify OT DMZs between, say, 4 or 5 factories, you could consolidate a whole lot of licenses and equipment in one location. And as an ancillary to that, you could also consolidate processes which demanded humans. So the thing that could save them more money most of the time was, in fact, unifying your OT DMZs. But to do that, you would need to be insane to establish a static SD-WAN across these things, because you now have a single very target-rich asset you've created, which is your linkage into all of your factories. So what people began to look for were moving target defense networks that could bridge these environments, and that has become a substantial source of our revenues, but it is much more recent.
If I can paraphrase what I hear Ian saying is, imagine you have a dozen, 12 manufacturing plants or water treatment facilities or something, 12, a dozen industrial sites. Classic sort of Purdue model says you have layers of networks inside the industrial network, and then you have a DMZ sitting at the site between the industrial network and the IT network, and no connections from the industrial network go straight through the DMZ into the IT network. All connections have to stop in the DMZ network. And this is seen as, a degree of protection, because an adversary who comes in and wants to manipulate the industrial network first has to break through the firewall into the DMZ network. And from the DMZ network has to break through a second firewall into the industrial network. But if you got 12 plants and you've got, let's say, a historian in each of these DMZs, because that's your focus of IT/OT integration between your plants and your IT network, you've got to have 12 historian licenses. And so the scenario here is put the DMZ into head office, put one historian in the DMZ for all of the industrial sites. Yeah, but now if someone breaks through the firewall into that DMZ, they have sort of one layer of defense sitting between them and all of the industrial sites. Instead of 12 targets, you've sort of reduced it to sort of one target or 1.5 targets to reach all those sites. And what he's saying is that because of that increased risk from having a single target, a single DMZ that has access to all the industrial networks, because of that increased risk, you see the moving target defense being dropped between that central DMZ and the sites to try and provide an extra layer of protection there.
Okay, so is it that having those 12 different historians and whatever is markedly less efficient than having 12 different, for lack of a better term, instances of this moving target defense? Because it still seems like we're centralizing one thing and decentralizing another.
Well, it depends. We're talking dollars here. Depends on the cost of the historian. Depends on the cost of the moving target defense solution. Depends on how many other servers you have in the DMZ. It might be more than a historian. There might be a manufacturing execution system. There might be who knows what. And once you start multiplying licenses by 12, depending on how expensive they are, it could add up. So this, it does sound like there could be a material cost savings by centralizing stuff on the IT network.
Right, and I get that. I suppose what I'm asking is, you can centralize your security in one place at a head office for the sake of efficiency, cost savings, whatever. You could decentralize among many different locations for the sake of security, but why are we choosing one of those for one solution and one of them for the other?
Most of the time, anytime we automate a process, we introduce new kinds of risks, sometimes cybersecurity risks, sometimes physical risks, sometimes new failure modes. And this is what engineers do. They have to evaluate the benefits of the automation, the efficiency benefits against the increased risk, and they have to take steps to mitigate the risk. And so what I see here in terms of moving target defense and this sort of central DMZ scenario is a new option that I didn't know existed until I heard, Ian presenting at the Gartner conference a couple of months ago when I tapped him and said, "Hey, you got to come on the podcast." So, I'm learning about a new tool that, I didn't know existed.
So that makes sense, but it sounds like we're still talking about, in your terms, human to machine interaction, remote desktop style interaction. Do you use the moving target defense system for instance, to connect the lift station to the SCADA system, through a public switched network?
The answer to that is nuanced. Most remote access most of the implementation that I have seen of moving target defense in cyber physical systems has been from an OT DMZ out. If you're inside the OT DMZ and traversing down into it, unless you're in fact traversing a public wire at some juncture, most of the time what you'll see is everything's privately networked, and they're not going to worry about that too much. They might need to, but they aren't. And they're just going to worry about the problem once it reaches the OTDMZ. The one exception to that I have seen a great deal of chatter around has been in defense, where you can't afford to make a certain set of assumptions, and where you might have the problem set of every single device that's out there is its own traffic node, or might want to be treated as its own traffic node, because there is no other resource available that can serve as a traffic node to establish these networks. So you'll see this in these discussions around the advanced battle management system, Project Overmatch, Mosaic, these large initiatives, which are quite public, about establishing a means of joint all-domain command and control.
Okay, so I mean, this is coming together in my mind. It's moving target defense is a technology that's been evolving from the military space into the industrial space. You live that. You're the vice president of the local association there. Can you look into the future for us? I mean, is there anything else happening in the military space that you see moving into industrial that we should be aware of?
So when people began to push aggressively, coupled with dollars, to fix the problem of, I need to apply moving target defense for communications amongst parties and devices in the defense world, you saw this scramble from manual solutions to automated solutions, and then solutions that could adapt over time, and then solutions that could accommodate first tens, then hundreds, then thousands of interconnected people and or devices. The next big push that I see happening is someone is going to have to solve the problem of, I have 1 million devices, and I don't necessarily know which ones I'm going to be able to access at any given point in time. And I need to be able to communicate with some, if not all of them. And in some cases, I can't communicate over a reliable set of comms channels. Instead, I'm going to be traversing, say, side nodes and then jumping up. So you'd be going from device A to device B to the internet, then back down into the unit that you wanted to reach. That problem set, if paid for, will lead to a series of solutions, some ugly, some not, that have a meaningful buyer in the form of IoT generally. And then going from IoT, you find yourself in industrial IoT not that long after. And fortunately, we have both been around this long enough to note that there is a predictable pattern between when defense says they have a problem, when standards start to appear, and when standards get fully implemented, and then when commercial solutions that aren't just trying to meet the standards but are actually really nice to use start entering the market at scale. So my guess is that over the next 5 years, that's the big one. And by the end of 2027, 2028, you're going to start to see a whole lot of solutions that apply moving target defense at the massive scale rather than the large factory scale.
So Nate, the massive scale industrial Internet of Things, the example that springs to mind is smart meters, or people call it advanced metering infrastructure, AMI. In a city, you might have 500,000, you might have 2 million of these meters. And in my understanding, some of them already can do, hey, look, I've got poor cell coverage or poor network coverage in, the 6 buildings in a corner that we have trouble getting to. So these meters will reach out over the radio signal and find each other and, find that one of them has connectivity into the cell network and the internet, and they will daisy chain their communications through each other to get to that one, to get out to the SCADA system, which sounds exactly like the scenario Ian was talking about. So, and there's been a lot of people writing about, concerns about smart meters and these AMI infrastructures, saying these seem like, singularly vulnerable targets because they're out in the world. Anybody who wants to can walk up to these things and touch them and potentially take them apart and hack them and who knows what. So, an additional layer or two of defense in there. This sounds like something that, might very well get adopted in that space, because they're looking for what can we do to, address this risk in this extremely distributed, millions of devices environment. I mean, you mentioned 800-160, NIST 800-160 a couple of times. Let me ask you about that. I mean, I had a look at the document. I confess I haven't read it cover to cover yet, but it's got the term security engineering in the title. And, in my understanding, engineering is about sort of predictable solutions to problems. You design a bridge to support a certain load over a certain period of time. And, if you mess up the design, engineering is a regulated profession in many jurisdictions, because if you mess it up, you put public safety at risk, and you can be drummed out of the profession to protect the public from mistakes like this in the future. And so in the security engineering, I interpret the term, when I've heard it used, to mean sort of deterministic solutions. Saying the load is the adversary, define a set of security load that a solution is going to, completely predictably, support over a period of time. Is that how 800-160 uses the term? What do they mean by security engineering?
Volume 2, which is where moving target defense came out, was presented. The full title, Andrews, is Developing Cyber Resilient Systems, a Systems Security Engineering Approach. The thing that was happening there was, up until the publication of that standard, you would find concepts related to cyber resilience spread out across any number of different standards. And the same thing was happening in other standards bodies. And what was going on was the way I think about cyber resilience is, if you stop just thinking about making your system difficult to be destroyed by an adversary, and instead start thinking about, make my system hard to kill. In other words, don't just worry about the fact that you might have an attacker outside the building trying to burn down your server farm, but also worry about the fact that your server farm might have been put in a closet beneath a bathroom. You will engineer a solution that is more effective at dealing with a whole host of problems, not just one. And that argument, I think, is congruent with the one that you've presented, and is congruent with what happened in 800-160 Volume 2. And then, because they didn't cover all of the things that I think they wanted to cover in a prescriptive approach, what 800-172 covers, which is the more advanced set of cybersecurity rules that you need to follow if you're handling controlled and classified information, but could equally be applied towards data flows that are transiting out of an industrial control environment, is they began to say, okay, right, you really must take into consideration a lot of the things that happen just on a day-to-day basis as a system degrades because of age, because of environmental factors. And if you have a system which doesn't die when one piece of it gets destroyed, or is not dependent upon a virtual machine running perfectly ad infinitum, you've built a system that's also much more tolerant to attacks against it and able to resist it and carry on functioning.
Well, thanks for that. Thanks for the pointer to 800-160. Mea culpa, I didn't know it existed. I am certainly going to read it and study it. It sounds like something that's very much worth going through. But we're coming on the end of our time here. Thank you for joining us. Before we let you go, is there a thought you'd like to leave with our listeners?
So I understand that a lot of the people that are listening to this are relatively new to the role of having to handle large bodies of operational technology. Everyone came out of IT, where you could implement large quantities of static defenses and get your job done. But it has been almost 3 years, since the baseline cyber resilience standard in the States appeared, calling for moving target defense. If you aren't using moving target defense right now, it's not like you're not a first mover. You're kind of beginning to fall behind the curve. So the thought I'd leave with you is this is not something that can wait until next year. You do need to start thinking about this now. You do need to start reading up on it. This NIST body of work is excellent in that regard. I'm sure that there are many a vendor out there who would be delighted to pitch to you as well. But this is something that you've got to start paying attention to now.
So, Andrew, what do you think about moving target cybersecurity?
Especially when it applies to remote access, it sounds like a good idea. I mean, remote access of any kind is, in a sense, uniquely risky. This is one of the big risks. Everybody kind of wants a little remote access because it makes their lives easier. Don't have to drive out to site. But, you're talking about computers on the internet controlling physical operations. Why is this a good idea? And so people put as much defense into that equation as they can. This sounds like a new layer of defense that I wasn't aware of. So I'm grateful to Ian for joining us and bringing us up to speed. The other thing I got out of the episode was references to 800-160 and 800-172, the NIST standards. I mean, I've read NIST 853. That is the sort of the standard list of security controls. Use antivirus here, use long passwords there, that everyone references. It's one of the Bibles of cybersecurity. I've read 800-82, which is kind of the application of 800-53 to the industrial space. Shame on me. I wasn't aware of 800-160, and it sounds like something I need to go read cover to cover. And, same for 800-170. So, I got a lot out of this, and I say thank you to Ian.
Agreed. Thanks to Ian Schmertzler for speaking with you, Andrew. And as always, Andrew, thank you for speaking with me.
It's always a pleasure. Thank you, Nate.
This has been the Industrial Security Podcast from Waterfall. Thank you to everybody out there listening.